Can you hear me? Sort of? Okay. All right. So, great. So I'm Bob Bonneau, and I'm the head of the Information, Decision, and Complex Networks Division at AFOSR. And for the next, day or so, we're going to talk about information technology. And I'm going to preface this by saying that information technology is an interesting area today because a lot of what's going on in it, people really associate with the commercial world. There's a lot going on in the commercial world. But I guess what I've really, learned, and the point's been driven home really, deeply over the last, since I've been doing this job and much before, is that the DoD has a critical role in defining what's next. Because in the commercial world today, there's a lot of emphasis on things that are, going to be, fairly near-term investments. But when you start to look long-term, there's not very many places out there that really think deeply about, for instance, how to advance the state of mathematics to get to the next state, next set of information systems that are going to be out there. So what I'm going to try to do today is essentially motivate some of the challenges that the Air Force faces, the DoD faces, and in general the country faces in terms of getting to some of these problems. Hopefully, you'll get a sense not just from me, but from the other program managers, program officers in RTC, how that's evolving here. So next. Okay, so you're going to hear from every one but two of our current program officers, and Bob Herklotz, who was on the schedule today, sends his regrets. He's actually recuperating, I think, as Dr. Mattson said, from a recent procedure. And so, and then James Lawton is inbound, I think, as Kyle Gresham said a little bit earlier this week. He's coming in from our European office to take over some of the things here at the Arlington office. But you'll hear from everyone else, and I think what I'm going to try to do is give you a sense of kind of how we cover the areas that the Air Force finds critical in terms of its next generation information technology. So to preface this, we are called Information, Decision, and Complex Networks, and I've talked about this before. Why are we called that? I mean, that's kind of an important thing to start with. One of the things that you've heard about here at Spring Review so far is that there are highly defined ways that people look at scientific problems in many of the disciplines. So if you were to take things like, we just heard from the physics division here, basically, there are well-defined, equations for electromagnetics. There are well-defined equations for most of the physics disciplines, and those models have, stood the test of time over the last, 100 years or more, really in terms of informing how science is done. But what we're facing in the information world right now is this sort of explosion of new systems that, in effect, don't have predefined models associated with them. Basically, these systems are, very heterogeneous. They're very distributed. Actually, Dr. Farouk talked about some of this earlier this week. And so basically the pieces of how to put together the information technology sort of science are in evolution right now. And I think hopefully you'll hear that as part of our talks. But information is, if you think information is an area, for those of you who are familiar with statistics, many of the distributional models and things are pretty well defined for, some sets of problems. But in general, as you move to decision and you put humans in the loop, in many cases, you need to actually learn what that model is, and you need to learn it online. going from the sort of discipline where you sort of predefine what those statistics are, sometimes from analytic models, to looking at how humans in the loop are really quantified in terms of their behavior, particularly when it comes to problems like autonomy, where they are as much a part of the system. The machine and the human have to interact in such a way that they get the best outcome for the the mission they're supposed to perform. I mean, that becomes a really challenging problem in terms of how to model that and how to model that online. And finally, complex networks, the program is the one I'm responsible for, has really been about starting from purely your measurement. So if I just start with not a lot of information about the system and I measure it online and I actually have to follow that model in real time, that defines a lot of the modern information problems, particularly in cybersecurity, in a lot of the problems in terms of our computational infrastructure, where in previous days we could verify and validate some of the models that existed there, but now the dimension of those models is so high, you really need to get effective ways to reduce the dimensionality on those problems. Now the good news is that mathematically, a lot of those mathematical challenges have been really addressed very effectively, and in not small part by the programs here at AFOSR in the last decade. So we have, and I'm going to demonstrate this, and the other POs will too, mathematically, we have new tools we didn't have 10 years ago because of what we've invested in here. And that's incredibly important because the customers for that are really broad. They range from the Air Force and the Department of Defense and all the way to just the industrial base of the United States. And I know that firsthand because I actually interact quite a bit with industry, and I interact across the DoD, and people depend on these things. So what I'm going to try to give you a sense of is how we put all those pieces together, both in the portfolios that you're going to hear about, and also just generically, from a technical standpoint, like what is this whole picture, sort of put together. So, so we'll talk about information first. I don't know if Dr. Nachman's still here, but I spent a lot of quality time with Dr. Nachman when I first came to AFOSR because I actually was a reservist here. We have some reservists here now. And I knew him well before that as well. But I mean, from that world, we had a lot of very well-defined, propagation models for electromagnetics. And if you have those kind of propagation models, there's a lot you can do with them because you can really define the problems very precisely. But at the end of the day, particularly when we get into problems like spectrum allocation, spectrum utilization for instance, the Air Force and the DoD, which are real challenges for the Air Force right now. And many of you are familiar, if you look at the sort of, high-level Air Force and DoD mission statements, they talk about, A2AD, right? And, this basically means in the context of spectrum that you don't have the resources you need, particularly in spectrum, to work with. So given that, how do you essentially electromagnetically manage an environment that is dynamically changing and increasingly contested, either because people just don't have to follow your spectrum policies or people are actively trying to deny you the ability to do your mission. The next area that we deal with pretty regularly, and this is implicit in the autonomy area, is looking at machines versus humans. Okay, when you actually start to look at the trade-offs between machines versus humans, there's a lot of literature out there today that really is defining this. And I don't, we have some of the folks from DARPA here across the hall today, actually, who are part of the DARPA Robotics Challenge. And we work very closely with them through the National Robotics Initiative in looking at kind of what machines are now capable of doing versus what humans do or have done sort of traditionally. And that's a rapidly changing area. And you don't have to go any farther than some of the recent press on what's going on in robotics to see that. So the question is, if we're going to, in real time, analyze from a mission standpoint, which has the lower risk, the machine or the human, how do we do that? How do we do that online, and how do we do that efficiently? So those are all really big challenges. They're very hard. I mean, there's no sort of golden bullet for that, right? There's no way to get that question succinctly answered through any one means. But mathematically, we've made a lot of progress, and you're going to hear about that. And last but not least, complex networks. So complex networks, when I started out, there have been a lot of programs that have looked at networking and communication. You've even heard about some of the more recent work in control theory and communication this week. What strikes me, though, is that until very, very recently, the ability to literally define your models, define your control, your models of your system, your plant, actually, and then validate those models, and then turn that around, verify the system performance, and manage it accordingly, if you know nothing about your system a priori, is a real challenge, or very little about your system. And given that those models can change dynamically, and this is certainly true in the case of cybersecurity, but it's also true just in the case of resource allocation management, how do you really define whether you've got a good model from measurement, and then whether that model is still valid, n time steps after you've actually started going along with your assumptions about what's happening in your system. And the beauty of this, the mathematics that we have, is math is a very general language to describe this. And so because we've advanced mathematically in this area, a lot of these tools, and I kid you not, I've done a lot of talks, although not as much recently because of the conference restrictions, but I've done a lot of talks in math departments around the country and internationally. And one of the things that I've really noticed is that this particular area is one of the hottest topics in mathematics. And as evidence of that, we have, the AMS is, I'm going to talk about this, but the AMS is actually, the American Mathematical Society, has really, a lot of the people in this program are recognized as having, put some of the more cutting-edge advances in mathematics in the last 5 to 10 years. So I think it's being appreciated in the academic community in general. So that's the overview of complex, or of information decision in complex networks. I'm actually going to jump into my own presentation next because Bob's not here, and as Dr. Metzen announced, we're sort of bridging the gap. So I think the best thing to do would be to sort of, I'll be happy to take questions at the end of that. I've actually been talking with Carlotta, and I've given myself 45 minutes to do both presentations, and I will make it. So, and this is just, it's the interest of time and brevity. Okay, so in past years, I've spent a lot of time talking about complex networks, and we've had some very basic goals with the program. And as we started this program, even some of the techniques I'm going to talk about today didn't exist 7 years ago mathematically. They just weren't there. And so we had to fill in a lot of gaps to get a consistent picture of how to do some of the most basic things in measuring heterogeneous digital infrastructures and predicting their behavior. Okay, I used to, I talked about some of the, the goals and the payoffs, getting information from point A to point B with a certain probability, not bits, but real information. I talked about managing infrastructures robustly. I talked about having a unifying mathematical model to really describe this whole process. And one of the things that has sort of come out of all that is that I think we do have, because of what's gone on in the program, sort of a continuous thread that actually I'm actually starting to see integrated into some of the college curriculum, both in the statistics and math area. And so instead of, I promised Dr. Metzen I would be, efficient in this talk. So basically, what I'm going to do is actually just, I'm going to give you a very, sort of basic overview, as I just did, of what complex networks is about. And then I'm going to create a thread from an academic standpoint of kind of all the pieces. And I think they actually do all line up for the first time. as one sort of unified discipline. And to that end, actually, there's been a number of journals that have actually been started in complex networks. I'm actually involved in editing some of them. The beauty is this is a field mathematically that's sort of beginning to mature, and it's really gratifying to see that, because at the beginning we couldn't just point to a journal and say, this is it, we're done. I mean, we didn't have the American Physical Society. We really had to build this into a sort of new approach. So I think from an accomplishment standpoint, I mean, we're not the only, or even we're a player, but we're not obviously not the sole player that's put this together. But the idea is that the mathematical community has really sort of embraced this, and this has helped. And certainly the other thing that happened when we started was the Army had also the network science program, and that has definitely helped us. We've worked very closely together with them, and I think that their efforts too have really I'm going to show you this picture, and this is the last sort of illustrative slide I'm going to show you in this entire talk. In the old days, I would have given you like all these sort of cartoony kind of pictures that would have described all the pieces of the program. I'm not going to do that. I'm just literally going to go through the sort of projects in the portfolio that correspond to each of the areas you see on the diagram in front of you. And the first part I'm going to talk about is measurement. Okay, so just measuring a system at all, and particularly digital infrastructures, is a challenge. And it's a challenge because you want to get a good model from those measurements, but the challenge is that it's not clear how much you actually have to measure to get that model, a validated model. And the question is, do I need to measure from now until infinity, to the end of time, to get a good model? I mean, we can't afford to do that. So step one is how to actually measure effectively to understand that you got the actual true essence of what you're trying to understand. The second thing that we're looking at is modeling and validation. So once we've made those measurements, is that a validated model? Do we trust it? The problem is right now with information technology, these models are dynamic things. They change over time. So a valid model now might not be a valid model in an hour or a day, and that's a problem, right? Because if I'm betting all of my mission performance on that model, I really need to know that it's a validated model. And so the question is, how do I do that online? How do I build a model and then sort of throw that model out and get a new model online in real time as things change? Right? That's another huge challenge. And finally, once I've gotten the model, I've taken my measurements, I've gotten the model, now what I want to do is essentially manage the system and verify its behavior. So there's always trust but verify. And in this case, basically verification, particularly in high dimensional problems, tends to be many people talk, for instance, in computer science, people talk about model checking. One of the more recent things with this program, we created this Foundations of Information Systems program, and we talk about probabilistic verification. Probabilistic verification literally is creating a distributional model for what's going on in the system, and then essentially model checking that, which tends to be an inference problem. That becomes it becomes literally a hypothesis testing problem. So, I think Dr. Faroux talked a lot about, how a lot of these disciplines are converging. She talked about control theory and optimization and decision theory and all of the pieces. So what we hope to do is really provide a unifying mathematical thread for all of that, and that's what I'm going to tell you about in the next 26 minutes. So let's start with measurement. Okay, measurement is hard, and high dimensional measurement is really hard. Now, you know, I've talked in previous years about sparse measurement. Okay, this is not, you know, this has been around for about 10 years. People have talked about it a lot. What they haven't done, however, particularly in the context of digital infrastructures, is measure bits. Okay, I mean, it's one thing to go out and measure sensor data. Okay, digitize it, have an A to D, you know, take video imagery, you know, all the things you would traditionally do sparse measurement on. But when you actually measure bits in packets, or you actually measure bits in, you know, computational infrastructures, like you would with a sensing system, which is really our objective, the question is, how do you reach into that space of bits and pick out the right ones? Okay, so Ping Li at Cornell is a very excellent and well-known statistician, and basically he noticed that in these computational infrastructures, one really efficient way of picking the right bits was to use something that computer science has used for a very long time in sort of all sorts of domains. You know, particularly when you're trying to verify that you got the code to compile properly, or try to verify the performance of binary images that you've got in your your computational process. He realized that functional approach using hashing could actually be a very effective way of measurement as well. And so this is one of the very first instances where these hashing functions were actually used to project onto these really high dimensional binary spaces, and then efficiently come up with a model, a distributional model, using a regression approach, which is the standard sparse approximation technique. And what he showed was, using this hashing approach, he was actually able to get much more accurate measurements with much fewer measurements, which really amounts to time, bandwidth, and the ability to really compact and characterize the data much more efficiently than you could with standard linear techniques, linear sampling techniques. So this is a big deal, because it's not about just taking any sort of generic sensing data and randomly projecting onto it. It's about using principled approaches to, in effect, create a functional, nonlinear functional sampling approach to take out the right bits. And this leads us into some really good work in terms of validated models once we get there. Okay. So now I have this really powerful technique of, or set of powerful techniques of reaching into my space of bits and actually getting the right ones. What's the next thing you have to do? Well, basically what you'd like to do is to, after you've done that sampling, divide up all those bits into parameters that characterize the basis of the model you're going to make. And so we use spectral decomposition techniques for that in many cases. And a lot of the literature, again, in sparse approximation has been around this L1 norm. Now, I won't go into the sort of great benefits of using L1 norms for sparse approximation, but what I'm going to say is what Rachel Ward at UT Austin did was, she found a really efficient spectral decomposition technique once you've done that sampling to, in effect, reduce what you've got in that really high dimensional space into a set of critical parameters that actually, again, lead themselves to a validated model. So Rachel's approach to sampling this space ended up improving the accuracy by orders of magnitude on, in this case, network data. And these are just, the original function that was being sampled is on the upper left, and the function that she used to, in effect, create that approximation of the original model, you can see that you get a much more representative model by using this approach than with any of the standard sparse approximation techniques. And this is with the same number of measurements, which are incredibly sparse. I mean, we're talking tens of measurements to actually measure tens of thousands of bits in some really high dimensional space. So this allows you the ability to measure really complicated spaces very efficiently and get accurate results. So I promise, actually, I won't tell you the person, but one of my PIs has often said, you know, math is something better talked about in private, right? So I hit you with the math up front. This will become an increasingly, you know, I won't say applied talk because we don't do that, but I'm going to show you that this evolves to some really critical capability that we need to actually do a lot of the things I was talking about in these information systems. So I've talked in previous years about topological ways of representing data. And one of the things that I talked about was actually having a taxonomy of all the things that you would ever measure. So recently, there's been a group of mathematicians who've really looked hard at integrating topological analysis with statistical analysis. And it's become a new field in statistics. It's called topological statistics. And now you'd say, well, OK, so what? Right? Well, topological statistics is now allowing us to look at the entire space of models that you would get from any data and literally understand how accurately the data you've measured fits into that space. So in a statistical sense, it allows you to calculate risk very accurately in really high dimensional contexts. And so so I mentioned that Ping Li's work and Rachel's work led to really good parameterization. Basically, once you've done those two steps, the next step is literally to topologically put all the pieces together. So you go from local to global. And these global representations can be very accurately parameterized. And this gives you highly validated models. And we know that because algebraically, there's just no other place for it to fit in this high-dimensional space. There's only so many ways your data can fit into this space. And the space is low-dimensional, so I can do it fast. I can do it computationally fast. And that means I can take really high-dimensional infrastructures, data infrastructures, collapse them down into very simple representations, and then use those and trust those models implicitly and do it really fast. So that goal that we were talking about in our program is this is how we mathematically do it. And by the way, this is new math. I mean, this didn't exist 5 years ago. So we have a whole crop of new American Mathematical Society fellows because of this work. So and this is getting used. I mean, this is very much in the mathematics literature right now. But basically, yes. So this is how you go from data to model, and your model is highly validated. OK, I promised I would stop with the math, and I'm not going to do that, but I'm going to show you some practical ways to use the math. So so the idea here is that now, if I have these sort of well-characterized algebraic and topological representations of my data, the idea is that you ought to be able to do stuff that engineers care about, right? Like, spectral transform. So we're all familiar with the DSP, right? So this group, actually led by Jose Mora from CMU and Alberto Grimbon from the math department at UC Berkeley, basically said, well, why can't we construct a new Fourier-like transform for these high-dimensional data sets and do so that what you're in effect transforming is the connected behavior of the structures I just showed you. So the idea is you've got what amounts to a graph transform. So instead of a Fourier transform, we can take any network of data and we can transform it into its spectral components and do it by literally the models that I just showed you and the structure of that data itself. And so we have basically what amounts to a Fourier transform for a graph. And that allows us to take really high-dimensional, connected, highly correlated data, which we couldn't really deal with before because there was no easy way to sample it. And we can simplify it down into what amounts to a new Fourier transform, a nonlinear, high-dimensional Fourier transform, and then separate good things in that graph from bad things in that graph. And this is a graph of actual wireless data. It was taken at CMU. And the wireless data has anomalies in it. And these where people are, in effect, trying to hack into your wireless network. And so basically what this technique, this transform, is showing you is the ability to detect those much earlier, much more efficiently, and much more dynamically than you ever could before because we have this technique. So this is kind of a, this is kind of a breakthrough. I mean, it's basically a nonlinear high-dimensional Fourier transform, and that's generally useful for all sorts of engineering disciplines, well beyond, communication networks. So, and again, these techniques are actually being now generically applied in all sorts of domains, from signal processing to information theory, and it was really because of that sequence of math I just showed you that we got here. So, okay. Okay, so now what you'd say is, well, okay, I can do all that great stuff you just told me about, but for instance, I would like to be able to put the amount of processing it takes to do that on my iPhone or my Android phone or whatever, because most of the things that we have to recognize, most of the data that we have to interact with, has to be, it's portable. It's stuff that you're going to gather in real time. You want results, and you don't want to spend all day, computing it. So, what this group, John Har and Sayan Mukherjee from Duke, did was, in effect, take all of the classical techniques we use, principal components analysis, singular value decomposition, they put it into the framework I just showed you mathematically, and then they brought that into a real-time target ID application. Now you'd say, well, that's nice, but it turns out, now I spend a lot of time now these days with the Assistant Secretary of Defense for Research and Engineering. They found this incredibly useful. And I won't go into the specifics, but the point is that we are in the process of, as the DoD, not just the Air Force, but the DoD, of taking these tools I've just shown you and coming up with ways, in this case, of doing real-time target ID in some very complex scenarios we could just not do it in before. So there are real benefits to actually going down this road, and we've talked about AFOSR being sort of the place where the Kalman filter kind of found its origin. We're finding that a lot of what we've got now is going well beyond. We firmly believe, and I didn't show it in this, and actually I think Tristan may actually talk a little bit about it, that we're actually getting to the next generation of things like the Kalman and particle filter because of this as well. So I've just shown you a couple, we started out going, okay, we're going to do communication networks, right? We're going to, look at how things, can be measured and so forth. And look what we just got out of it. We got something that's basically a new Fourier transform, and in effect, we're getting what amounts to a new Kalman filter because we did this. So that's why math is transformational. It actually allows us to do this sort of fundamental advance in all these different disciplines because we looked at these problems in a different way. Okay. So another way you can use this stuff, which is incredibly important, is up until now, networks have been a pretty static thing. And so if you go on the internet right now, that internet was pretty much the way it was when somebody logged into it 10 years ago, maybe. I mean, it's probably bigger, but the core components are pretty much the same. What's happening now is we have something called software-defined networks. Software-defined networks mean that you can essentially reprogram the router that you're dealing with in real time. And as you reprogram the router in real time, what happens is that the classical architecture of the internet will change on the fly because, you have to change. For instance, if you have more traffic load coming from the West Coast to the East Coast, you want to change your routing policy to reflect that. And so the applications are literally reaching down to the router and changing the way the router does business. Now you can think, man, there's just so many problems with that. Like, how do I deal with the security issues, among other things? But again, these techniques that I just showed you sort of come to the rescue. Because, in effect, what you have here is the ability not to just measure stuff and model stuff. But what I mean by manage is look for the stability properties, both the local and the global stability properties of an infrastructure because you measured it, and algebraically characterize them and find out where your network is basically going to start dropping packets and collapsing next. And so, for those of you internet aficionados out there, if you're familiar with Border Gateway Protocol, I mean, when you really look at the internet, there's two kinds of things. There's a sort of core routing functions, and then there's a sort of everything else that sort of sits on the periphery of it. BGP is a big deal because, in effect, people talk about the dark internet or whatever it is, but basically, it's the part of the internet that is not part of the core routing table, so it's aware of the whole thing. People at the edge of the network essentially send stuff to each other. And we don't know a lot about that, but it affects the traffic loads back at the core of the network quite a lot. And particularly in DoD and Air Force systems, when these kind of protocols get used, so I hook a lot of things to a distributed infrastructure that might be pretty heterogeneous, these things can collapse because I put too much stuff on that network. And so this technique, actually put together by Boon-Thao Liu, based on the stuff I just showed you, measurement, modeling, validation, is a verification engine. Literally, it's the same kind of verification engine you would use in software model checking, statistical verification technique, that essentially it says, look, is my network in a stable resource configuration, secure configuration, or is it about to collapse? Can I predict that? So you look at the structure of the algebra that I just showed you before, and using that, you can actually tell whether your network is going to die or not. So this gives you a predictive capability on your network. Okay, so now we've gotten a couple direct examples of how this really, all this stuff really benefits you. But why stop there? Okay, so we've heard a lot about quantum networks or quantum information systems. I have a new MURI kicking off. One of the things we realized very early in this is that if you look at the next generation digital infrastructure, lots of people think it's quantum. But to do a quantum infrastructure, basically you've got to measure it, right? Because this is a really dynamic, statistical thing. And if you take a look at Tatiana's pictures of cold atoms, that's in effect what things we measure stuff like that. So this MURI team, which is actually led by Dirk Englund up at MIT, we're having our kickoff shortly, has the ability to literally inject real entangled quantum states into optical networks. Those states go out over the infrastructure. They can be measured in real time. And then if there's some perturbation in whatever those optical states, those those entangled photon states are doing, basically, because they're entangled, an interruption way over here basically results in somebody over here knowing about it. But that's a big deal, because what we've heard up until now is this sort of, well, how do we route all the information back to some local place and then process it and then send it back out? Well, here, basically, because everything's entangled and it's entanglement at a distance, the promise is that in effect we can monitor our infrastructures or even resource our infrastructures, and if I change something over here in my quantum network, stuff over here basically will be validated or checked or guaranteed. So, but that's a big management issue, right? I mean, I've got all these states floating around. I got to know where they are. So the beauty of this is that because we have these algebraic techniques that I just showed you, and these statistical techniques, and these topological techniques, we're actually applying those directly to be able to be sort of the global manager of the quantum states over a quantum network. And so we aren't just doing sort of digital stuff with these techniques, these mathematical techniques I showed you, but we're actually enabling the implementation of some of the newer optical quantum techniques, physics techniques, over these infrastructures, and using the math to essentially validate the quantum states and the models of those quantum states, so that our information is, again, we're stable, resourced, and secure on our infrastructure. So, and trust me, this is coming to a router near you before you can imagine. In fact, there's a startup right now. It's not quite up and running, but you will be able to buy this capability shortly. this is really exciting, right? I mean, so now what we're really looking at is the future, generation of the physics of the infrastructures that we're going to build, both from a computing standpoint and a networking standpoint. And so all of the mathematics that I just showed you becomes the basis for understanding how that infrastructure's working at a physical level. And that's really important for all sorts of reasons. Okay, but I don't want to slight the sort of cloud, digital, sort of classical information community out there. So one of the things that we do is we do a lot of joint programs here because we're centrally located here in Arlington. And one of the cool things about being here is that I've worked with DARPA for a really long time. But when they approached us about doing this graphs program, they said, well, we like your complex network stuff, but we'd like to bring that into practice, particularly when it comes to cloud computing and large infrastructures. And we're wondering, how we would take that mathematics and actually apply it to, for instance, if those of you who are familiar with MapReduce, the way that cloud infrastructure sort of resource, their processors and their memory over distributed, networked data centers. How do you actually do verification and model checking on that kind of an infrastructure? That's really what they were after. So we needed a strategy for doing that kind of model checking and verification. And so we started taking the techniques that we had sort of worked on piecewise in complex networks and started mapping them out to approaches to actually model check cloud infrastructures. And what's coming out of that is actually what amounts to a new MapReduce engine. So instead of MapReduce, you're going to have a new sort of, it's not, we don't call it Hadoop, but basically it's a way of doing implicit verification of your computational process over a cloud infrastructure in real time, and it's implicit in the way that cloud architectures. So now you can start to see, well, maybe I could put all these pieces together, right? I could take the the quantum piece, and I could put the cloud piece together with it, and I could look at the physical layer, and I could start to look at the spectrum issues and the resource allocation issues, and really sort of, and that's the point, because these are holistically, these are all the things that the DoD and the Air Force have to do to guarantee a mission happens on an infrastructure in a contested environment. And so that's really kind of where we wanted to go with all this. So the underlying mathematics becomes the basis for doing that. Okay. So for those of you who know me, I came from RI, okay, which is in Rome, New York, which has a lot more snow than we do right now, even though you don't believe it. They actually, I've been working with them for a long time, and they started, they became believers, right? They're believers in complex networks. So they started the Center for Complex Networks at Rome. And this is actually, these are some of the people in my program, but not exclusively. And they're actually growing. So they hope to make this an AFRL-wide center that actually takes these techniques that I just showed you, because of all the things you can do with them, embeds that into your information infrastructure and allows it to actually do business. And these other groups that I showed below here are other lab tasks that I have. But these other lab tasks essentially are partnering with the folks who are part of the Center for Complex Networks, and they are integrating this into all of the things that we have to do in AFRL, among other places, for transition in information technology. So, if you get some useful math, people will use it. So there you go. Okay. I always like to talk about how we collaborate with other agencies. With another hat, I'm the co-chair of the large-scale networking group for OSTP. So we do a lot of national initiatives. One of the biggest national initiatives that we've been asked to do, most recently, is in software-defined networks. But a lot of things happen at that, in that domain. And another big area that's happened is the National Robotics Initiative. So whether it's autonomy, which I talked about, or it's software-defined networks, which I also talked about, defining your model, representing it, validating it, controlling things, validating your risk, all that stuff is useful in many domains. I certainly we work very closely. We have a program here in spectrum management with DoD CIO, which is becoming quite successful. We work with the Software Engineering Institute at CMU, led actually by one of our former AFRL commanders. We are part of the OSD JCTD Mathematics Challenge. Tristan will talk about that a little bit. We have the DARPA Graphs and COMEX programs that we support, I support. I'm part of the Network Science and Cybersecurity CTAs for ARL and ARO. We certainly, commercial stuff, which I didn't talk a lot about, but getting this stuff into the commercial domain is a big deal. And so an LTE, the new wireless standard, is an even bigger deal. So how do we do that? We work with OD&I and the IC Basic Research Working Group, certainly NSF, NIST, and DOE, because they're all part of the OSTP group. I can't ignore this. We had 6 new American Mathematical Society Fellows in the last year. That's a new thing for AMS, by the way. Before you could get a Fields Medal, but that was about it. Now you can get fellowship in the American Mathematical Society. So, and some of these people, these are all like, National Academy, some of these people are National Academy and whatever, but because they did this math, and it's kind of the cutting edge of the math, and this is being recognized in the math community as a big deal, which means people in math, who would normally be more pure, are really starting to understand that this is vital to stuff we have to deal with right now in really practical stuff. So maybe that's another connection, and I think certainly NSF is appreciating that. We're starting some new initiatives with them because this is happening. And I like to get out, I like to talk to people. Haven't been able to do it as much as I have in past years, but people want to know about this stuff, particularly both in the engineering and math communities. So we're trying to get out and tell them. I'm hoping that this is I do think that the critical mass and the momentum for this sort of approach is now sort of rolling along pretty well, but happy to get as many people who care, because you're here and you're listening or whatever, involved in it. And with that, I'm probably about 58 seconds, 1 minute over. Thank you. Any questions on any of those 2 talks? Yes, sir.
I'll just have a question on the measurement where you're analyzing the bits and so on. Mm-hmm. You first have to convert the individual bits into something higher level, or
this is literally on the
particular, structure within the bits.
This is literally structure in the bits, and that includes randomized or non-randomized bits.
So there's some aspect of pattern recognition involved?
Yeah, I mean, this is it basically, yeah, it's part of, we want to call it estimation and detection, maximum likelihood testing, or, ultimately pattern recognition. But it's building models directly from the data and then understanding whether the system conforms to those models. And so, unlike sort of classical target detection or things you would think about in pattern recognition, you're literally looking at 2 incredibly large models and going like this and saying, yes, these are equivalent. Mm-hmm. So it's higher dimensional than you would sort of classically do in pattern recognition.
All right, okay.
Any other questions? Okay. All right, with that, I would like to introduce Dr. Kathleen Kaplan. She's going to talk about systems and software.